Hello everyone, this is Yifan from Well Canal Medicine. Today I'm going to talk about clinical natural language processing and deep learning in assisting medical image analysis. The motivation of this talk is quite straightforward. In the general computer vision domain, we have seen a great use of neural network and deep learning techniques on different image processing tasks. For example, image classification, object detection, or caption generation. One reason is that there are a number of big annotated image datasets that are publicly available, such as ImageNet or Microsoft Coco. But in the clinical domain, we haven't seen the same level of success. This is partially because there are less large annotated medical image datasets to fulfill the data-hungry needs of deep learning models. On the other hand, we know that hospitals have already accumulated a large number of raw images, such as radiographs. So the problem we want to address here is how we can construct a labeled medical image dataset to fulfill the data-hungry deep learning needs. For nature image annotation, we can use crowdsourcing. For example, we can given a picture on the left, we can put it online and ask what is in this picture. Then we know that there's a cat. But this crowdsourcing approach for collecting nature image labels is not applicable for medical images. There are a couple of reasons. Number one, it usually requires domain knowledge to annotate medical images. For example, when you see the chest X-ray on the right, I guess fewer people, unless you are a physician or a radiologist, fewer people will know whether there's a cardiomegaly in the chest X-ray. And number two, there are also issues of security or privacy. It is much harder to put medical images on the internet and ask people around the world to annotate them. So both of these reasons make it very hard to construct a labeled medical image dataset. What alternative way we can look into? The answer is clinical reports. We know that all medical images have clinical reports that are associated with them. So if we can find a way to extract the information from the clinical reports, then probably we can automatically construct a weakly labeled medical image dataset. So here I want to show you an example of chest X-ray with its report. The report says cardiomegaly. Findings include cardiomegaly, otherwise normal lungs and contours. There's no evidence of focal bone lesion. So from this report, if we can extract the findings, for example, the cardiomegaly, then we know the label of the chest X-ray on the left, which is a cardiomegaly. So based on this idea, in this talk, I will present two projects or two directions. In the first project, I will describe a rule-based system to extract findings from radiology reports and show how we can use the NLP, the clinical natural language processing techniques, to construct a large-scale chest X-ray dataset. And in the second project, we want to extract not only the findings, but also the attributes that describe those findings. Some examples of attributes include the size of the finding, the location of the finding, or the severity of the finding. So I will describe how we use a deep learning-based methods to extract those attributes to construct a label dataset with richer information. Now let's talk about the first task. The first task is to extract findings like cardiomegaly from the reports. But if we simply apply name entity recognition tool on the reports to extract all findings, we will also extract the lesion in this reports, from these reports. Then we create a mistake because the report says there's no evidence of focal bone lesion in the image. So here we call the cardiomegaly positive findings and we call the lesion negative findings because it is ruled out by the radiologist. And we definitely want to differentiate the positive findings and negative findings. Otherwise, the downstream applications like image retrieval may return many irrelevant results if we did not distinguish the positive and negative findings. We read a lot of radiology reports and find that there are much more negative findings in the clinical text than from the general text. More formally, we call a finding negative if it is ruled out by the radiologist, such as no evidence of focal bone lesion or clear of acute infiltrates. Besides negative findings, there are also a lot of uncertain findings. Here we call a finding uncertain if the radiologist is suspicious of that finding. So some examples include possibly small left pleural effusion or may represent small nodules. So those are uncertain examples of uncertain findings that we observed from the radiology reports. Therefore, the natural language processing task here is to differentiate the positive findings from the negative findings and uncertain findings. Here I want to describe a two-pass approach to achieve this. So in the first pass, we use the name entity recognition tools to detect findings from the reports. At this stage, we simply extract all findings. We don't care whether they are positives or negatives or uncertain. And there are many name entity recognition tools that we can use. We can either use a rule-based recognition tool with a control vocabulary, or we can use some machine learning-based methods to detect those findings from the reports. And in the second pass, we differentiate negative and uncertain findings from the positive ones. And here we can apply rules on universal dependency graphs to differentiate them. I will describe more details in the next slides. The universal dependency graph contains vertices and edges to represent the syntactic and the semantic information of a sentence. Vertices are words or phrases labeled with information such as a part of speech or name entity mentions. So in this case, in this sentence, lungs are clear of acute infiltrate or pleural effusion. Lungs are clear of, or they are words in the graph. And the acute infiltrates and pleural effusions are two phrases. They are also vertices in the graph. And these two phrases can be detected from the name entity recognition tool I described before. Besides vertices, there are also edges to represent type dependencies from one vertex to another one. So for example, there's an edge from the words clear to the words lungs with a typed dependence n subjects. It means that in this sentence, the word lungs is the subject of the sentence. We also have the conjunction or coordination construction in this sentence. So from the typed dependencies, we also know that the phrase acute infiltrates and pleural effusions are coordinated with each other in this sentence. And those information is very helpful when we apply the patterns on the graph. After we get the graph, we can define patterns to differentiate the positive and negative and uncertain findings. For example, we can define a pattern clear of something, and we apply the pattern on the graph. And we find that the pattern match two phrases at the same time. Then we know that both aqueous infiltrates and pleural effusions are negative mentions or negative findings in this sentence. And through this process, we can distinguish the positive and negative and uncertain findings. From this example, we can also see the reason or the motivation of using dependency graph rather than the surface text to do the distinguish. This is because by using the syntactic or semantic information, we can use less patterns to capture more text variations that cannot be done by using only the text surface with regular expression. So in this example, we only need one pattern clear of something, and that pattern can simultaneously apply to two phrases in this sentence and extract and do the detection. Otherwise, if we use a regular expression, this task is quite a challenge, because if we want to detect whether the pleural effusions is negative or not, we need to skip the words between the clear and pleural effusions, and we don't always know how many words we need to skip in the sentence. Here I want to show you several rules that are frequently observed in the radiology report. For negation findings detection, the most common rules are no disease, without disease, clear, free, or disappear of certain disease, or without evidence of disease. For uncertain findings detection, the common rules include cannot exclude, concern for, could be, maybe, or difficult to. So those rules are frequently appeared in the radiology reports. We name the methods NACBEL, and we make the code and rules public available. We hope that other institutions or other researchers can apply our tool on their own or on their in-house datasets and release the weekly label datasets to the public. We hypothesize that the release of the labels will be easier than the release of the whole reports because of the protected health information embedded in the radiology reports. We also applied our tool NACBEL on the NIH CXR datasets to generate labels. So this NIH CXR dataset consists of more than 100,000 frontal view X-ray images with 14 common lung diseases annotated by the rule-based system. We released this large-scale label dataset in 2017 with the hope that the academic or research institutions across the country will be able to teach a computer to read and process X-ray. Besides NACBEL, there are other NLP tools to extract the findings from the radiology reports, and there are also other large-scale CXR datasets that make public available in recent years. So here I listed two famous CXR datasets. One is CXPERT, which was developed and released by the Stanford group, led by Matthew, who is the speaker, one of our speakers in this tutorial. Their group developed the CXPERT labeler, which is also a rule-based system built on top of a NACBEL. They also developed a deep learning-based methods, a BERT-based methods called CXBERT to detect the 14 common lung diseases from the radiology reports. The other data set is called Mimic CXR database. It was developed and released by Johnson, who is also one of our speakers in this tutorial. So taken together, we have at least 3 large-scale CXR datasets with high-quality labels of 14 lung diseases. And through this process, we have already seen a big improvement of using deep learning to detect lung diseases from CXR. This is how we can use NLP techniques to extract the findings from the radiology reports. In the next steps, we want to extract not only the findings, but also the attributes that describe those findings, such as the finding size or its location. So in this way, we can probably construct data sets with richer information, and we believe such richer information will be more valuable for medical image analysis. Therefore, in the second part of my talk, I will describe a work that uses deep learning method to construct such data sets with richer information. To show how those attributes can contribute to the image analysis task, let me first give you an example of lesion images retrieval. The image on the left is the query image, and the images on the right side are the retrieved images. Here we use not only the image, but also the attributes like right, which is the location, or rib, which is the body part. We use those attributes to help us retrieve images from the database. From this example, we can see that we can retrieve more diverse images that are not similar to the query image, but share the same semantic meaning. From the previous example and many others, we know that the attributes in the clinical reports, in the radiology reports, are also very important. So now the question is how we can utilize the NLP techniques to extract those attributes that describe the findings. Let's take a CT image and its reports as an example to demonstrate the relation between the reports and the image. In the CT image on the left side, there is an area of interest marked in green. The radiologist then wrote a sentence to describe this green box. The sentence says, within the right middle lobe, there's a stable nodule that measures this size. And then the radiologist will link the sentence to the box by inserting a bookmark. It's also marked in green. So from this bookmark and the sentence, we know that the type of the bookmark is a nodule, and its location is within the right middle lobe of the lung. So in this products, we call the right middle lobe and nodule the attributes that describe the bookmark. And the task is to extract them from the radiology reports. If we use the name entity recognition tool to extract all attributes in a sentence, we would make a lot of errors. So first, there might be multiple bookmarks in one sentence. Like in this sentence, long plural, smaller dependent, left plural, modularity, for example, bookmark A, and periodic, bookmark B, the smaller junction, possible scaring, bookmark C. There are 3 bookmarks in this sentence, but we are only interested in bookmark C because it links to the CT image on the left. Therefore, the first challenge here is to find which attributes describe which bookmark. Like in this example, the left plural modularity, they describe the first bookmark, but not the bookmark C. Second, there are also uncertain attributes mentioned in the sentence. Like in this example, it says possible scaring. So it's uncertain attributes that describe bookmark C. Therefore, the challenge here is to differentiate the relevant with the irrelevant and uncertain attributes. So in order to do that, in order to differentiate those attributes, we treat this problem as a relation classification problem in natural language processing. So we first create all pairs of bookmarks and attributes in the sentence. And then for each pair, we use a deep learning model to judge if the relation between the bookmark and attribute is irrelevant or relevant or uncertain. Like in this example, we have 3 bookmarks and we have 5 attributes. So together, we have 5 candidate pairs for bookmark C. And for each pair, we use a deep learning model to judge whether there's a relevant relation or irrelevant relation or uncertain relation between bookmark C and attributes mentioned in the sentence. Our approach therefore consists of 2 steps. In the first step, we use the name entity recognition tool with the ontology to extract all the attributes from the radiology reports. And in the second step, we use a transformer-based model to distinguish the relation types. There are many deep learning-based methods or other machine learning-based methods that can do the relation extraction or relation classification. Here, I just want to emphasize that for this problem, the input is a sentence with the attribute and the bookmark annotated, and the output is a 3-class label, which are relevant or irrelevant or uncertain types of relation between the attributes and bookmark. Because of the time, I will now talk about the details about the architecture of the model we developed. But I want to emphasize it's a transformer-based model, and we make this for the same reason. We make the code and the model public available so that others can reproduce the results and also use the model on their in-house datasets. And we applied our model on a dataset called deep lesion, which is a large-scale and diverse database of lesions in CT images. It consists of more than 30,000 annotated lesions. And by using our tool, we create a set of 171 common attributes based on the red legs ontology to describe those lesions in the datasets. And this dataset is also publicly available in 2019. To summarize in this section, I demonstrate two use cases to use clinical natural language processing techniques and deep learning in assisting medical image analysis. In the first project, we use a rule-based system to extract disease or findings from the radiology reports. And in the second project, I demonstrate how we can use the deep neural network to extract attributes that describe the findings in the radiology reports. So by using the NLP techniques, we can automatically create large-scale fine labels datasets, and using those datasets, we can do some medical image analysis tasks that cannot be done before. So these two examples demonstrates the useful of clinical NLP in assisting medical image analysis. So at the last, I want to thank my colleagues and also the findings that supports those projects. From the talk, probably you have a sense that the clinical NLP is really helpful in assisting medical image analysis. So in my lab, we also have new opening positions for postdoc to continually explore different areas of clinical NLP in assisting medical image analysis. If you are interested, please feel free to shoot me an email and we can go from there. So that's all for my talk. Thank you for your time, and I would like to take some questions.